Hello everyone. Today we're going to talk and continue our discussion on computational complexity. So far we talk about analysis of the time complexity of the selection sort, insertion sort, and exchange sort. We're going to talk about permutation and inversion terms, and we're going to see that with these terms and with their concepts, how we can find a lower bounds for solving or for simple sorting algorithm. Okay, so let's do it with one example. Let's say you are going to sort three numbers. You have n1, n2, and n3. Okay, so and we want to say how many combination or permutation of these numbers we have. So the permutation of these numbers can be this triple n1, n2, n3, or n1, n2, n3, and n2, n2, n1, n3, n2, n3, and n1, and finally n3, n1, and n2, n3, n2, and n1. So as you see, there are 6 permutations for these three numbers that we have here. Okay, and it's really easy to see that like the number of the permutation is equal to n factorial. So here n is equal to 3, or the number of items that we have in, let's say, in our array. So the permutation is equal to n factorial. And it's really easy to see that because we have n option to choose the first number. So we have n option. For the second number, we have between the n minus 1 other numbers that remain. So it's going to be n minus 1, and then we just continue until there's only one number is remained. So that's going to be equal to n factorial. Okay. So one other thing is that we are going to assume like these n number n1, n2, n3. Okay, they are like the natural numbers. Okay, and let's start from number 1. So let's say we have let's assume that n1 is equal to 1, n2 is equal to 2, and n3 is equal to 3. Okay, so this assumption shouldn't hurt our discussion, okay, on finding lower bound on the the sorting algorithm. Okay, just for showing some examples and how with this example this is gonna work. So with these numbers that we have here, okay, so n1, n2, and n3, so we have 1 and 2 and 3, we're defining another concept called inversion. So these are we had these 6 permutation here. So these are the 6 permutation that we define here. And let's say that we have a permutation. Okay, let's, for example, we have a permutation of 1, 3, and 2. Okay, so this is a permutation of these 3 numbers 1 and 2, 3, and we have here. Okay, so we call a pair of Ki and Kj an inversion, okay, such that also we have I is less than j. Okay, if we have K of j is less than K of I. Okay, so we are calling this pair of Ki and Kj, okay, in an inversion. If we have if I is less than j, okay, and K of j is less than Ki, okay. So in this permutation that we have here, okay, so this is a permutation of 3 numbers, 1, 2, and 3. So we can see that the only inversion that we have here is the inversion or the pair of 3 and 2. And here is because the index I for this permutation is equal to 2. Okay, let's start assuming that we are starting at index 1, and j is equal to 3. And as we know, so also we know that the K of I is equal to 3 and K of j is equal to 2. So that like has this, we have this condition that k of j is less than k of I, and also I is less than j. So this 3 and 2, okay, is an inversion in this permutation that we have. Okay. So now with these things, okay, we are gonna like see that how this is related to the sorting. So a sorted array, okay, let's say we have these three numbers of 2, 3, and 1. Okay, so let's say this is an array. This is an array we have. So, and as you see, there is a like there is an inversion here that is 3 and 1. Okay, so a pair of 3 and 1 is an inversion. Okay, when also we have this another inversion that is 2 and 1. So there are two inversions in this array that we have, or this permutation. So here we have 2, 1. Also we have 3, 1. Okay, so that's in permutation. Like there are two inversions. If we sort this array, okay, easily we see that this like this is a sorted array. So 1, 2, and 3, and there is no inversion in this array. Okay, so that's the relation of the inversions in sorted array. Okay, now let's look at this theorem. So we are saying that if there any algorithm that sorts n distinct keys, okay, so let's say we have an array of size n, and removes at most one inversion, okay, after each comparison. So we said that the inversion is when we have the indexes I and j, so such that I is less than j, but the key allocation I is greater than key allocation j. So by removing that, we mean that we are sorting that part of the array. That means that if I is less than j, then the value allocation I will be also less than the value allocation j. So any algorithm that stores n distinct keys and remove at most one inversion after each comparison. So in the worst case, it needs or it requires to at least do n multiplied by n minus 1 divided by 2 comparison. And this is an average will be n multiplied by n minus 1 divided by 4. So we'll see that how how we can prove this theorem, okay, for the best case, for the worst case, and also for the average case. Okay, now let's look at this example, okay, before going to the proof, before the proofs of the worst case and the average case for the theorem 1. So here we have these three numbers. So we have an array of size 3, so n is equal to 3. And we have numbers 2, 3, and 1. Here are the two inversions that exist in this array. So we have inversion 2, 1, pair 2, 1, and another inversion or pair is 3, 1. So we need to at least make this one fixed. Okay, so to remove this inversion, we will have the pair, this should be transferred to 1, 2, and also we need to have this 1, 3. Okay, but this doesn't mean that like after removing this conversion, we are gonna the array will be sorted, okay, or no other inversion will be created. But we're saying that at least we need these two. So to show that the worst case, okay, the number of comparison will be n, at least gonna be n multiplied by n minus 1 divided by 2. Okay, so that's the worst, like the minimum. Okay, so that's gonna be the minimum. We need to find, okay, we need to find a permutation of this number, like this array that we have, an array, okay, of the arrays of n numbers, okay, and say that there are a permutation that has n multiplied by n minus 1 divided by 2. Okay, so what's the case? Because as you see at every, okay, the theorem says that if an algorithm, okay, removes at most one inversion, okay, after each comparison. So we're going to say that how much comparison we need. Okay, it's going to be at least n multiplied by n minus 1 divided by 2. So here in this permutation we had 2, 1 here. So if we can find a permutation of n numbers, okay, then it's going to be n multiplied by n minus 1 divided by 2. So we are going to see these numbers, let's say we have number n, then n minus 1, n minus 2, and goes up to 1. We're gonna prove that this is the permutation, okay, that at least requires n multiplied by n minus 1 divided by 2 comparison, okay, to remove all the inversions. So we can easily prove that using induction. Okay, so this is the again, this is the case. So we are going to show that if we have a permutation like n, then n minus 1, n minus 2, and 1 onto 1, then at least we require n multiplied by n minus 1 divided by 2 comparison to remove inversions. And it's easily you can see that this is actually an order, an array in the reverse order. So the worst case, it happens when we have an array in the inverse order. So we're going to prove this one using the induction. So assume that n is equal to 2. So our array will be number 2 and 1. Okay. So, and here we'll have 2 multiplied by 2 minus 1 divided by 2, that is equal to 1. And as you see here, the only inversion that we have is the pair 2, 1. And with simply just having that 2, 1, 2, that's going to be 1 and 2, so it's going to be sorted. Now we are going to see for n equal to k, and assuming that for n equal to k, it is at least k minus 1 divided by 2 comparison. So that's the minimum or the at least the number of comparison. Now we're going to see that also let's write the number. So it's going to be k minus 1, k minus 2, until we reach the number 1. So that's an array of size k. Okay, so that's an array of size k, and in its reverse order. Now we're going to see that what's going to be, we're going to show that. So this is induction, okay, base, okay, induction base, and this is our induction hypothesis, and this is what we're going to show. So show that this is also true for n equal to k plus 1. So when the number of numbers that we have in our array is k plus 1, so we have something like here. So k plus 1, k minus 1, k minus 2, until we have this number 1 here. So for this k number that we have here, we had to do at least k multiplied by k minus 1, okay, divided by 2 comparison. Here we have, let's write it here. Here we have, let's see how many inversion here we have when we add this number k plus 1. So when you're adding this number k plus 1, this is an inversion. So k plus 1, this is a pair of nk, because k plus 1 is definitely bigger than k. Then we have k plus 1 and k minus 1, until you reach the k plus 1 and 1. Okay, so that's the number of inversions that that has been added, okay, to the number of inversions that we have, that so far was equal to k multiplied by k minus 1 divided by 2. So at least the number of comparison, okay, will be equal to k multiplied by k minus 1 divided by 2 plus the number of the inversions that are added. So at least we need to do the comparison to do the inversion to remove these inversions. That is equal to k. So we are adding k other inversions, so at least we need k more comparison. So simply if you just add these numbers together, so we will have k, let's use this one here. Okay, it's gonna be equal to k plus 1 multiplied by k divided by 2. So that's the proof. Let's prove the that in the average case, okay, the number of comparison over at least we're gonna do n multiplied by n minus 1 divided by 4 comparison, okay. So for showing the average case, okay, let's see we have a permutation, okay, in the number that we have that is in this form. So we have like the K1, K2, K3 to Kn. Okay, so this is a permutation, okay, and definitely we can have another permutation, okay, with this n number that is in this form as Kn, Km, and n minus 1 until we have this K1. Okay, so we call these let's call this P1, this permutation 1, and this is P2. So we call this P2 a permutation or a transpose of the permutation P1. Okay, so because every number is is reversed in the order, so there's a transpose of this one. So now assume that we have a pair, okay, of R and S, okay, R and S. So either let's say that R and S, okay, R and S is either RS or SR, okay, is an inversion. Okay, so one of them at least just only one of them, okay, is an inversion. And the reason we were saying that only one of them, this is because we assume that the keys are distinct. Okay, so R and S, okay, this is because R is not equal to S. Okay, so because R is not equal to S, then we have only one. So if we have the pair RS, okay, definitely the SR is it's transpose. Okay, so we have only one inversion in like this, for example, this permutation, or on its transpose. Okay, so not more than one. Now the question is that we're gonna see that how many permutation we have like for the numbers from 1 to n. Okay, so for if we have a number n, okay, we will have n multiplied by n minus 1 divided by 2, okay, that is the number of pairs that we have. And how we can see that the number of pairs, okay, we already showed it like as part of the proof for the worst case. Okay, we showed it for the like the n equal to 2, n equal to k, n equal to k plus 1. So this n multiplied by n minus 1 divided by 2 was like the total number of inversions that may exist between like the permutation and its transpose. So definitely for the average, okay, we are just dividing this number by 2, so we will have n multiplied by n minus 1 divided by 2, and divided by 2, that is gonna be n minus 1 divided by 4. So that's gonna be like the proof for the average case.